So, good afternoon to everyone. My name is, as the guy in the t-shirt, sorry, I forgot your name, said, my name is Prykhodchenko. I work as a software engineer at Allegro. And for some of you who do open source, you may have noticed some of my activities at OpenStack projects as a core reviewer. Currently, I work mostly on Ralph data center asset management system. It's also open source, so you can also check it out. And today, I'm going to talk to you about how we manage workloads efficiently in our infrastructure at Allegro. And I would like to start with the foundation of the issue we have. And the foundation starts with Allegro being a really big company. It's one of the biggest e-commerce platforms in Eastern and Central Europe, and it's #1 platform in Poland. That results that we have more or less 20 million of active user accounts, and we serve more or less 20 million of transactions per month. That's pretty good numbers. And in order to do that, we run several thousands of assets in our 2 data centers. And on normal day, we have around 30 gigabits per second traffic on our load balancer endpoints. All the services are served by around 600 microservices, but since we have been in continuous development for the last 18 years, maybe last 19 years, yeah, that's the new presentation, we have some monolithic leftovers, of course, and we have to deal with all of that. So, and when we do all those services, we think how we are going to put them into HA workloads. We are thinking about something like this. So there's usually some sort of load balancer or several load balancers with some leftover failover strategy. And they are covered by a whip, and the whip allows us to actually enable that failover strategy. And there is some instance pool of the actual service and those instances are actually doing some job. And based on the needs, the load balancers distribute workloads based on some load balancing algorithm like round robin, least con, or whatever. And then we actually implement the service and try to put that into production environment. And that's where the reality strikes us the first time, and the overall idea starts to crack. And that happens because in the past, we used to think about services as they were deployed to bare metal servers. And we could easily estimate the capabilities of the hardware, and we could easily plan the workloads, and we could easily configure the load balancers to more or less efficiently distribute the workload to the specific instances. Those times have come, and right now, every specific service runs in sort of virtualized environment, like virtual machines or some sort of containers, and that gives us very great freedom from the deployer's perspective, because we should not worry about any dependencies and any conflicts. But performance-wise, we never know who runs with us on the same hardware and who implicitly shares very valuable resources with us. Those resources could be CPU, those resources could be disk, network, I/O, any I/O basically. And we never know if several or one or more instances are running on the same hardware with every specific instance, or whether or not there are some neighbors that could be sometimes some noisy, you know that. The situation is even worse because in modern days, people often use containerized orchestrator tools like Kubernetes and Mesos, and those tools spawn, respawn, kill, reschedule containers whenever they need. And so we can never estimate a homogeneous environment for our instances. So then, even if you plan another thing, even if you plan your infrastructure, hardware infrastructure, in the way that it's homogeneous, so it all has the same hardware, you will end up with some eventual hardware upgrades or eventual repairs, and then some of the hosts that you have in your data centers will become less powerful. Some of them will become more powerful than the others, and you can never predict which of the instance has more processing capabilities. So you put that into production. You enable users' workloads into that architecture, and since some of the instances are deployed into less powerful hosts and some of them are deployed to more powerful hosts, and since the distribution of the instances is uneven, some of the users experience lags. So some of the requests start to take lower time, some of the requests start to take bigger time, and users are not as happy as we want them to be. And while users' happiness is only partially related to the EBITDA or operation costs, then from the hardware operator's perspective, some of the hosts become overloaded because they are not as powerful, but they run too many instances, and some of the hosts become idle, and because they run just a little of instances and they are actually powerful, and that is directly related to operation costs. And we would expect the load balancer would be to be able to distribute workloads, not based on some balancing strategy, but basically based on the capability of every single instance which is running inside the containers or inside the virtual machines inside the hardware. And then the users would be getting more or less the same response time, and from hardware perspective, the utilization of the hardware would be much more optimal. So as you can see, we are running our infrastructure for the last 19 years. So we most certainly faced this issue, and we had to find a solution. And before I explain that solution to you, I would like to say one thing. Like, there is no silver bullets. This solution, you should not go after this conference and say to your managers or other guys, we should do that. You should every time you should analyze the things and see if it fits to you. It fits to us, it fits to some other guys, it may not fit to someone else. And while this is a Python conference, I'm not going to go very light on Python. Some of the things we saw were good, some of the things we saw were nice, some of the things were not as good. So basically, this is going to be a pragmatic presentation about how we resolved this issue on our infrastructure using Python, and what good parts and what not so good parts we faced. So I would like to start with general requirements you would usually put to some solution for the problem like that. And as I said, no, not as I said, I forgot the name again, sorry. That guy said, I'm a follower of the DevOps philosophy, and so is our team. And we decided that we should not reinvent the wheel for a lot of times, and we should reuse the existing components of our infrastructure, and we should reuse the capabilities of the existing systems that are available in either open source or in the market. And while we do reuse existing elements of the infrastructure, we would like to keep the mission critical elements safe. Never ever we wanted to spoil our load balancer and let those 20 million users and leave those 20 million users without being able to buy things. So we grow constantly. The number of microservices I showed you, it's like 600. It's the number from the last year. I think now it's 800 or even more. I could actually implement a counter in the presentation. It would still be the right number. So we grow. The number of services grow. The number of instances grow, and we should be able to incorporate that growth. And we should be also adaptive to changes, because we use different technologies. Some of the services may rely on different metrics, some of the services may rely on different systems, and we should support all that. Another thing, which is, I think, actually the most important from that list, is that we should not break the isolation, because the isolation which I mentioned is a good thing, because it allows us to not only keep the deployment safe, but it also allows us to keep the services safe. And that's a good part, right? And we don't want to propagate any errors that happen in one place to the other services. So regarding the reusing stuff, when we are speaking about some production-grade architectures, apart from load balancers, Sorry. Apart from load balancers and VIPs and some instances, there are usually some other existing components. And those components are usually some service for collecting metrics, some metering service like Graphite, like Prometheus. And there's usually some discovery service like Zookeeper, like etcd, whatever. And those components are most likely to be present in every production-grade infrastructure. And so basically this scheme of a typical service architecture looks like this. And if you look at that and try to think, what are we going to reuse? The most straightforward way is to make load balancers smarter. So load balancers may know about some capabilities and stuff, but that's arguably a good idea since mission-critical elements like load balancers should be as simple as wooden spoon in order to be able to operate normally with no outages. If you complicate your load balancer, you get outages. You lose money, you lose your job, you lose your company. So we don't want to do that. However, most of the production-grade load balancers like HA Proxy or Nginx, they have this balancing strategy that is called differently depending on the balancer, but it's sort of like round robin, but it allows you to set the weight to every instance, so the instances with bigger weights get more requests. And given all that scheme, and given that most of the load balancers have this load balancing strategy, we can start working on. So basically, our solution is the following. We call it instance score, by the way. And in this presentation, I'm going to use the word score and weight, and that's interchangeable. So we switched all our load balancers to this round robin with weights strategy, right? And since load balancers are were already being configured from these discovery services, that's what you usually do when you have a discovery service, right? You have some list of services, list of instances in the discovery service, and you have some key value parameters for that. So we just add another parameter like weight for every instance, and load balancers start getting that weight and apply that in their configuration. That's a shortcut, actually, because most of load balancers cannot get configs from the discovery service. You usually have some other thing that gets the config and puts that into discovery service. But just for this simplification reason, let's assume that load balancer gets this configuration. So now the quest is just to calculate that weight. And given that we have metering and discovery services, we can do that in the following way. So something should get the metrics from the metering service. Based on that, it should calculate the weight for every instance that is available for a service and put that to discovery service. And then when the load balancer gets its new config, it can apply those weights for the instances and start doing smarter balancing. So it would be that simple, and the presentation would be over at this point. Like get instances, get metrics, calculate weights, and push them in an infinite loop. But it was not that simple, of course, and it was not that simple, right? Because instances and services are not constant in modern environment. You can never assume that there is a service that is running all the time. You can never assume that the service has constant number of instances. That changes. Metrics maybe and most likely will be delayed. No metering service is giving you metrics in real time. That's it. Different services may have different metrics to rely on. If some services rely on CPU power, then you would need to collect CPU usage metrics. Some of the services may rely on disk I/O. Then you collect disk I/O, right? And sorry, technical issues. Nope. Yep. Sorry. Then, when we calculate the weights for services, for instances, we do not want to apply every weight we calculated to the load balancers. We do not want to kill our load balancer by constantly changing their settings. We have to find the balance between the optimum utilization of power or optimum utilization of disk I/O and not killing our load balancer. And the worst part is nothing of that could be estimated. So you cannot take, and you cannot see which number of instances would a service have beforehand. You cannot see how the metrics will be delayed, and so on. So in order to comply with those hard problems we found, we decided to separate every component of instance score into components. And first of component is instance watcher. And that's a component that is going to run asynchronously, and it's going to get, periodically, it's going to get instances from the discovery service, format them accordingly, and put into some sort of channel, right? The channel is then could be read by another separate component called MetricWatcher that for received instances gets the metrics from metering service and formats them and puts to the channel. The channel with metrics is listened to by the weight calculator that calculates metrics, puts the weights to the score channel, and then we have the last decision element, which also runs asynchronously. It decides whether or not this change has to be set up to the discovery service. So we call this 4 components scoring runtime, and it allows us to perform instance scoring for one specific service. So it only works for one service. It's very important that all of those components you see, they are stateless, so you can restart them and nothing happens. Like stateless with a star, actually, because the calculator may have some state, like you could calculate some average, but then when you restart it, nothing should happen. And they should all run simultaneously and asynchronously. When we started to think what we should implement that, what technology we should use to implement that, I wouldn't lie to you, we didn't think of Python first. We thought of Golang. And every Python conference should mention Golang once. Don't worry, we'll return to Python very soon. We thought about that because these components fit into the conception of the concept of the Go routine very well. Like they run simultaneously, they can use channels for blocking I/O to read some data, and when there's some data, we can continue, right? So that's how it more or less it looked with the Golang. Like you don't have to understand the code. It's just a simple infinite loop of a MetricWatcher that is listening to a channel. You can see that. When there's some data, it gets some metrics and pushes it to the metrics channel. But then I decided to try to write it in Python. And because Python has this awesome technology called asyncio, which you probably heard about. And these individual components fit into the concept of asyncio coroutines. And every coroutine is running asynchronously, and you could use asyncio queues in order to have this blocking I/O, so you can wait for the data. And so when you have the data, you do some operation and then push the your data to the channel and wait again. So this is the same code that is of the MetricWatcher that is written in Python with asyncio. So again, that's simple. You have an infinite loop. You await for some data available on an instance channel. As soon as there is some data, you get some metrics from the metric channel, from the metric service, and you put that to the metric channel. Again, if only it was that simple. The code looks readable, but there is a big trap. And the trap is that, unlike Golang's Go routines, coroutines and asyncio are not scheduled preemptively. And that means if you block something, if you have a blocking call, nothing works. Like only your coroutine works at a time, and you can block everything. So, and in this case, you have this trivial line that gets configuration from the gets metrics from the metering service, and it actually blocks everything. So with asyncio, you would probably have to write it like that. So the standard approach is to take some sort of pool executor, like this is the process pool executor, which executes blocking calls in separate processes, and put the blocking call right there. And then the code looks sort of ugly and like Golangish, right? In Python, we like to write beautiful code. Again, there is a standard, de facto standard approach in asyncio to put everything that is blocking into sort of prepared asynchronous clients. And this is the code for score applier. When you can see, we put the score not by putting the blocking call into the process pool executor, but we use some sort of asynchronous client that we prepared. And given that you have prepared all the asynchronous clients for all the external services, for all the external I/O, you can get the same beautiful code, and that now looks more beautiful than in Golang, and works with the technology we know. There are a few important points for that. So, as I said, everybody should be aware of blocking calls. If you block anything, you're in trouble, because nothing works, and this element of the infrastructure is mission critical. Thank you. You should do no heuristics on error handling. If something fails, something goes wrong in one of your components, you kill the component. Then you propagate the error to the scoring runtime, and you kill the scoring runtime. So you should not even try to restore the things. Because you try to restore the things, you may get some bad state somewhere, and you don't know how it's going to go in the future. You are not going to try to restore from errors. You kill it. And one scoring runtime, it should be simple. Like, it should be like a series of those infinite loops that do one simple task and score instances for only one service. No ifs, nothing. And when they score one instances, every scoring runtime score an instances of every specific of one service, we would still want to score instances of different services that have that could be spawned, respawned, killed, and rescheduled. So we need something that will orchestrate our scoring runtimes. And for that, we decided to create sort of scoring Runtimes Orchestrator, and it does three things. The scoring runtime orchestrator, first, it reads the configuration. It could read it from the configuration file or the database or whatever, and the configuration file has really small content, and the content is service pattern that matches some of the names of the services, and the configuration of every component that should be in that for the scoring runtime for those services that match the pattern. So let's say we may have services that match Allegro frontend star, and they use Graphite as MetricWatcher, and they use calculator that calculates the scores based on the CPU FAIR algorithm. I will explain that algorithm a bit later. And we may have another service pattern like Allegro backend star that uses Prometheus as metering, as MetricWatcher, and that uses round-robin calculator that doesn't calculate anything but just assigns constant weights to all the instances. The second thing the orchestrator does is it gets to the discovery service and it gets the list of services. Then it matches that with the list of services or with the list of patterns from the configuration, and it goes to reconciliation. Reconciliation means it looks over the scoring runtimes and it kills the scoring runtimes that shouldn't be running but are running. Then it starts the scoring runtimes that should be running but are not running because they were not started or because they failed before, because we killed them because of the error. And the third step of the reconciliation is to look over the running scoring runtimes and check if some of them are having the same configuration as specified in the configuration file. If not, kill the old one, start a new one. That's called the reconciliation. In this way, as you can see, if we have a small error in one scoring runtime, like in one component of scoring runtime, we kill the whole scoring runtime. During the next reconciliation, it gets spawned again. So this is how we achieve the constant production for these runtimes. And the code is again simple. What I like about this approach actually is that the code is always simple. So you have sort of infinite loop again. The code reads the configuration file, reaches the configuration service and the discovery service, and goes over the scoring runtimes. It kills and unnecessary runtimes, it starts new runtimes. I didn't put the code for configuration much in here just for the sake of the presentation. You can imagine it's, again, the same simple. But, as I say, different services may need different requirements. Like I explained, we may use Prometheus for Allegro backend, and we may use Graphite for Allegro frontend. And how we enable to do that? And there are actually different set of dependencies that the services have, like discovery service, metering service, different calculators, etc., etc., etc. And we learned it in a hard way that we should always opinionate interfaces for that. So if you want to make a thing extensible, and this is a critical part of the code, opinionate an interface there. So if someone wants to build a calculator, or a discovery service client, or a metering service client, they should follow the interface. Otherwise, you should not even accept that. And in Python, there's a way to do that. There's a built-in library called ABC, which provides us with an abstract base class, meta class, which, when used, allows us to get some class and mark some of its methods as a specification. So if somebody does not specify, somebody inherits this class and does not have all the methods we describe, they cannot even create an instance, they cannot even create a type. It fails as soon as you try to run this code. And it's much better than you get strange runtime error when the instance core is operating. And then when you allow people to build components based on your interfaces, and you allow, let's say, to move those components to different packages, Python provides us a good way to not hard code imports there. That way is called entry points. And entry points is, if somebody of you doesn't know, entry points allow you to have a specific name assigned to a specific part of the code, like a function or a class. And then when you operate when you run the code, you can get that code, import that dynamically using the name. So let's say by importing the console, it's not like you write import console, but it's a bit different. But you can import this class, discovery console discovery service, by using the name console and using this namespace. So in this way, you could achieve extensibility. Right, the calculator. It's the most crucial part of the scoring process, and I promised to explain you how we built that CPU fire algorithm. And it's like the most complicated part of my presentation, but it's like, again, that simple. So let's say you have a set of instances running, and they all have different CPU utilization. So we decided to put that CPU utilization on some scale, and then if we get some average or some other value and accept that as a fair value, we could say that this value is the value the instances of the CPU usage is the value the instances should be using, but they are actually using another one, and it's not fair for them. So then we take some scale of the score, of possible scores, but please know that this is not percentage score. This is just some numbers. Bigger score or bigger weight means you get more instances relatively to another instances. Smaller score means you get smaller amount of requests relating to another instances. And we match that fair value of the CPU utilization to the middle of that score or weight scale. And that means if some instance has already this CPU utilization, it gets to the middle of the score scale. If it gets another one in another CPU usage, it gets to a different place on the score scale. And this is how the CPU fire algorithm works. And I would like to show you the effect of that. So this is the chart, two charts actually, from our production environment. This is one of our mission-critical services running here. And this is the chart for about 6 days. You can see some peaks and some lows. We have very regional traffic, so the lows are when the people sleep in Poland, and the peaks are when they buy stuff on our platform. So until some point, you can see that all the instances have the same weight. You don't have to see the number. You just have to see the weight is the same, more or less. Well, not more or less, the same. At some point, we enabled this CPU fire algorithm, the CPU fire calculator, for that service and start scoring weights for the instances. And as you can see, from this point, every instance has its own weight. The colors only represent instances from different data centers. Don't bother yourself about that. Just you can see that every instance has its own weight now. So if you look below, you can see the CPU utilization for instances of the same service for the same period of time. And you can see that before we enabled the calculator, some of the scores, some of the CPU usages for the instance varied a lot. Like here, well, I can tell you, sometimes it varied from 1.8 to 0.75, and that's a big difference. So after we enabled that, we can see that the CPU utilization chart narrowed. I like this chart very much. I mean, this is how you see, at this point, we started saving money on our operation cost. And that's it. So conclusion. No silver bullets, as I say. Good parts for that was we did proactive load balancing. We didn't wait until the things broke. We tried to reconfigure the things when changes were happening. We separated the instance scorer and instance scoring process from the critical parts. You see, we didn't change the load balancer, networking, nothing, just implemented a very small thing aside. We have small number of dependencies. In our case, we have 0 dependencies. We use everything using standard library. We allowed to extend that, and we allow to this even works for every service, not only your custom service. You can put, let's say, MySQL slave services behind the load balancer, and the scoring will work the same way. However, no silver bullets. You should be very careful about how you estimate your weights. This is one of the earlier charts from our production, and we really struggled to try to balance the weights for one of the services, and it doesn't work for everything. It works in 90% of the time, which is good for us. This is a point when I could start Holy War here, probably. Again, this is the thing that we found out while writing this solution, and this doesn't go to any other solution. So we found out that Python is really great for this thing, for writing solutions like that, because it's extensible. It allows you to use rich data structures. It allows you to use great libraries. And Golang doesn't have that. No. However, what Python lacks is good preemptive load balancing, and asyncio is a very dangerous thing to write in tools like that. If you allow people to extend your systems, you never know if they block something, if they will miss one blocking call and you will have everything blocked. So be careful and choose the technology. We frankly decided to stay on Golang just because of the sake of the blocking calls, because you never know when you block stuff. So anyway, thank you for your attention, and all the questions are welcomed.
Thank you, Roman, for the presentation. Any questions? Please raise your hand, stand up, and remember to hold your mic horizontally so we can hear you. Thanks.
Hi.
Hi.
I have a question regarding the times. How many times do you do the scoring? So is it a fixed time, for example, every 2 seconds, 10 seconds, 1 minute? Or if it's dynamically, you use a manual approach, like you see the graphics and you say, hey, let's put more time or less time? Or is it a system that dynamically calculates the time that you use to set the new score, the new weight?
So thank you for the question. So every component except the instance watcher, in our case, is data-driven. So when there is data on the channel, we do work. So if the score applier sees that the score has changed, there is a new weight on the channel, it goes to a discovery service and sets the weight. Given that the change is significant, we don't want insignificant changes. Instance watcher Well, we are scoring every 60 seconds. We didn't find any issues in that. Maybe it's possible to score more often, but we have a lot of instances, so we don't want to set too many weight changes to the load balancers. So it's of course possible for a discovery service to push the data to instance watcher, and then as soon as you get instances, let's say, you will get new scores. The orchestrator, in its way, runs every 10 minutes. So it doesn't hurt for us if something is not scored for 10 minutes. You just get a little bit uneven workload distribution, but a little bit.
Thank you. How do you, like this? Okay, okay. How do you test your calculator when you first implemented it? Do you have some sort of automated testing for it? How do you test all the infrastructure when you do changes to the algorithm of the calculator especially?
So basically, we have our test environment, and we may run we just deploy things to test environment. If it breaks, nothing happens. But we have unit tests in both Python and Golang, and like the algorithm is the thing that could be tested with solely unit tests. You don't have to put an algorithm in an infrastructure to test it because it's how you say it. It has no side effects. It's a pure algorithm. So
you basically wait for the data to come and see if it is doing well.
Yeah.
And if it is not, you just change it and you just take a look.
Yeah, right. But we can also do some testing based on the data we get from MetricWatcher. So we can get, let's say, we can get instances. We can disable, let's say, this score applier. We can choose the no op score applier that doesn't do anything, and we could deploy to the even to production, and that will work.
To see the difference?
Yeah.
Okay, gotcha.
So
Thank you.
Because you can interchange every component, you can do the testing by just specifying correct score applier.
Okay, thank you.
Thank you. So nobody's gonna bash on me for Golang, right?
Yeah, I have a question.
Right.
For the scoring, are you using what kind of? Is that a linear score? Is that something that on the edges punishes these instances that are using more, or how does it work?
So if they're using more CPU utilizations than the other, we just even that. So as you can, not sure how it's going to be faster. So our task is not kill or somehow say punish the instances. Our task is to make every instance feel comfortable. So if the instance is using a lot of CPU power, that usually means that it's on the edge of failing. You can actually see here, probably, some of the instances lived for a while and then died. And that's probably because they were overloaded a lot. And so the score in our meaning means that we are trying to set the score for every instance to have the fair amount of traffic from users. From other services, because it's not all users all the time.
Okay, so thank you very much, Roman, for your presentation. A big round of applause.
Thank you.